We are continuing with the lecture about measures of associations, and as a reminder, we started talking about the measures associations for the design that allows you to calculate new outcomes incidences. يعني عم نحكي على الcohort and RCT. We discussed how to calculate the relative risk and how to calculate the odds ratio, their interpretations, how to declare if they're statistically significant, either using the p-value or calculating confidence intervals. The concept behind a confidence interval, we discussed it, being the estimate plus or minus the statistical test times the standard error. And we said what influences this test is how confident you want to be. The more confident you want to be, the bigger the test, and therefore the wider is the confidence interval, and therefore the less precise is the interval. On the other hand, the standard error is directly inversely related to sample size. The larger the sample size, the smaller the standard error, the smaller the width, and the more precise is your confidence interval. We're continuing the lecture. So the next thing is how would you calculate measures of association if your exposure is a multi-level exposure, meaning it's not only present absent, but maybe there is a dose effect as well. So maybe you want to compare those not taking the drug versus those taking a low dose, medium dose, and high dose. So over here we have an example, but for smoking. And on the bottom you have the non-smokers, the light smokers, the moderate smokers, and the heavy smokers. And the first column is the incidence of lung cancer for every group. Still, we're dealing with the cohort. The total of heavy smoker is 4,308. The moderate smokers 4,386, and for light smoker 9,022. The non-smoker 51,477. I did not calculate the absent because when we calculate a relative risk, you don't really use the absent. You're just going to calculate the incidence in the heavy smoker, yani 30 over 4,308. For the moderate, you can also do the same thing, the 19 over the 4,386. The light smoker, same thing, and the non-smoker, the same thing. So you're going to calculate for incidence or for risks. And what you could do is very simple. You just use one of them as the reference. Typically, it's going to be the non-smoker as your reference. And you're going to calculate a relative risk light smoker versus non-smoker, moderate smoker versus non-smoker, and heavy smoker versus non-smoker. And therefore, you're going to end up with three relative risks. So on the next slide, I'm doing the calculation. You can see that for the so I'm using the non as my reference. For heavy smoker, these are the risks I'm calculating. The risk for heavy smoker, I mentioned earlier, it's 30 over 4,308. You get the number. For non, 60 over 51,477, and then you calculate the relative risk, and it comes out to be equal to 5.97. And let's say 6. Therefore, heavy smoking raises the risk of cancer 6 times, or the risk of the risk of lung cancer among heavy smokers is 6 times greater than that of non-smoker. That's the 6. And as I said, you can do that for moderate smoker versus non, and you could do that for light smoker versus non. And in that specific example, you can see that moderate smoker versus non, the relative risk is 3.72. And for the light smoker, it's 1.05. Comparing these relative risk, you can see that light smoker versus non-smoker, the risk increases only about 5%. It's a very small increase. If you go to the moderate smoker, the relative risk is 3.72, yani the risk is multiplied by a factor of 3.72. And when you move into the heavy smoker, the risk is multiplied by a factor of 5.97. Obviously, there is some sort of a dose uh, response relationship with the smoking. So again, here I'm going to take you back to the Bradford-Hill criteria. Remember, one of the Bradford-Hill criteria is dose response, our biological gradient, meaning that the more the the higher the level of exposure, the higher the risk of the outcome. So that is an illustration of a dose-response relationship between smoking and lung cancer. Obviously, you can calculate for each one of them a confidence interval to determine if they're statistically significant. And my guess that the first one is not going to turn out to be statistically significant, but the two others will be. But I'd have to do the confidence interval, or you can do you can get a p-value also to declare if they're statistically significant ولا لا. Okay, so let's see a straight application for the relative risk and odds ratio that I prepared on Excel sheet. Basically, just showing you again the things that we have discussed, but using an Excel sheet so that things are automatically done. The Excel sheet I prepared is here. I just need to let me just making it fit the screen. Yeah. So this is the general setup of the relative risk that by now you are familiar with. Exposed, then the not exposed, and then you have the new. دايما بقول new لأذكركم إنه we're talking about cohort or we're talking about RCT. So these are the new cases showing up in every group. So that's just the general setup. Over here I have actually an example. And in this example, my total is 1500, 550 in the exposed, 950 in the non-exposed. And I split the numbers inside um, in a way that I can yeah, just as an illustration. Okay. Now, over here, I have created a formula. So if I click on this cell right there, you could see the formula right here. So this is the risk in the exposed, meaning the 150 over the 550. And over here, you have the risk in the not exposed, the 200 over the 950. Okay. And I'm making it on purpose to be a formula. And I just put the risk in the exposed على not exposed to get the relative risk, and the relative risk comes out to be 1.295, يعني about 1.3. So there is a 30% increase in the risk of the outcome in the exposed versus the non-exposed. Then over here, what I'm doing is I'm calculating the confidence intervals, and by clicking, you can see that I'm actually doing some I'm doing the formula. So you don't see the actual cells because they're over here. Okay, so the P and the N is over here. That's where I'm doing my formulas. Okay, so the 90% confidence interval for this relative risk is 1.16 all the way to 1.45. If I were to calculate a 95% confidence interval, I'm going from 90 to 95 to 99. Obviously, I'm gaining on confidence, so I'm going to lose on precision, and my interval is going to get wider. And therefore, if you look at the interval, 1.6 is going to drop to 1.13, 1.45 is going to go up to 1.48, and finally 1.09 to 154. Okay, now, so over here you have the test value. I've discussed in class that the Z value for the 95% over here, right here, that's 1.96 in the formula. And I told you, كل ما بيكبر الconfidence, كل ما Z value بيكبر. So actually these are the value of the Z. So this is the Z value for 90%, this is the Z value for 95%, and this is the Z value for 99%. You can see how it is increasing. Okay, and the A value I told you about it is the natural log of the relative risk. So that's this cell right here, the standard error I've calculated using the formula we also covered in the lecture. And it's just formula plug and chug just to see how things are going to change as I'm going to change maybe a little bit the sample size. We'll see that in a minute. But hopefully what I wanted to say here is that if you look at the confidence intervals, they're all statistically significant. Okay? معناتها if you will to evaluate the p-value, remember the alpha for this one is 10%, the alpha for that one is 5%, the alpha for this one is 1%, and they're all statistically significant. معناتها your p-value not only is less than 10%, it's less than 5%, and actually it's less than 1%. And that's where over here I'm doing the chi-square, I'm getting a p-value for that chi-square. And the p-value comes out to be 0.061. That's the p-value for this relative risk over here. It's highly statistically significant. But the point is, if you look at this p-value, it's actually less than 1%, less than 0.01, which is exactly what I predicted using my confidence intervals. Okay. So next, what I did on this Excel sheet is that I repeated the whole thing, the whole process. Um, okay, one last thing in case you're wondering what is this. This is, remember the D. So if you look inside, you'll see that there's a calculation where I'm multiplying the standard error by the Z. Okay, every time I calculate the standard error by the Z, and then there I could do the A minus the D. So this is the D, and the D is changing according to the level of confidence. And then you're going to do 1 minus. We fee the standard error, and you can see this is the formula of the standard error that we discussed in class. Okay, I wrote it as a formula over here, but this is exactly what we talked about. So I have the parentheses, the 1 minus the risk in the incidence divided by the number of incidents in the exposed plus the 1 minus the risk in the not exposed divided by the total outcome in the not exposed, and you take the square root of all of it. This is the formula. You can go back to the formula and see it. But I'm just saying that I'm doing it as a formula so that I can get the numbers automatically. Okay, and last thing, the chi-square. Come in, I'm calculating the chi-square based on the formula for the chi-square. If you want, I can share with you the formula, or you can go back to your notes for PHA 205, or you can Google the chi-square formula. Anything would do. All right, so next thing I do, you can see over here, I have n times 2. So what I'm doing is I'm increasing my sample size. I'm multiplying my sample size by 2. So hopefully everything is going to be multiplied by 2. If I do that, so let's click over here. This one did not change. This is n equal 1. That is everything the same as we had before. Over here, everything is multiplied by 2. And you will notice that if you multiply everything by 2, the risk in the exposed, the risk in the not exposed, and the relative risk are not going to change. They're going to remain the same. Okay? And they ought not to change. I mean, that's what should happen. I mean, if you take a bigger sample size, the estimates are supposed to remain the same. However, notice what happens to, let me take you directly to the standard error over here. So the standard error used to be 0.067, now it's 0.047. It got smaller, and that's what we were predicting, right? Kilma standard error, Kilma sample size increases, the standard error decreases because it's inversely proportionate. And therefore, if you look at what is happening to the confidence interval, so if you compare the 90% confidence interval here to the 90% confidence here, you will notice that this one is actually narrower. بدل ما يروح من 1.16 all the way to 1.45, it's going from 1.2 to 1.4. It's not a question of only being narrower, but because it's the confidence interval of the same relative risk from the same data, kind of the same data, but the n is larger, um, the center is still the same, 1.295. This is the center, and therefore the lower and the upper confidence interval compared to these ones, this one is going to be a bit higher from that one, and that one is going to be a bit higher from this one. Okay, and also now let's compare the 95% to the 95%. You will see it's narrower, and if you compare the 99% to 99%, come in, it is narrower. Why? And you should know by now that it's narrower because the sample size is bigger. Also look at the p-value. What happens to the p-value? The p-value is much smaller now because as sample size increases, the study has more power. وكل ما study عندها more power, it's actually the p-value gets so smaller. I'm going to do now next the opposite. I'm going to make my sample smaller. So بدل ما to multiply it by a factor of 2, I'm multiplying it by a factor of 0.2. Okay. So again, this is the original data here. And now multiplying that by 0.2, I'm making things smaller. So بدل a total of 1500, I have a total of 300. And the risks are not changing, and the relative risk is not changing. However, look at the standard error. The standard error for the original sample size was 0.067, as I mentioned, but now the standard error is 0.164, much bigger standard error. And therefore, if you compare your confidence intervals when your sample size was 1500 to your confidence intervals when your sample size now is 300, you will obviously see something very clear, that the confidence intervals are becoming wider, much wider. In fact, much wider to a point that you lost statistical significance in all of them. All of them are crossing value 1, and therefore all of them are no longer statistically significant. Yani remember the alpha here is 10%, 5%, 1%. All of them are crossing 1. So your p-value is greater than 1%. Actually, your p-value is greater than 5%. Actually, your p-value is greater than 10%. And sure enough, if you look at the p-value we got from the chi-square, the p-value is 0.2196, greater than 10%, exactly what we predicted. And therefore, if I were to give you the p-value and I were to ask you about the confidence intervals, you should tell by yourself that since the p-value is 0.22 تقريبا, you would know automatically that all the confidence intervals here are going to cross the value 1, meaning they will not be statistically significant. So this is just an illustration of the things I covered in the previous lecture. I've talked about it, and here I'm showing it to you on Excel with the formula. I'm thinking maybe I can actually post this and you can come in and change the values. So if you're interested in changing the values, let me see how you can do that. There must be a, yeah, over here. You just divide this by 5 by dividing the value. So by dividing, maybe I'll alternate this formula so you just include here what is the factor and then everything changes. I'll see if I can do that and I'll put it for you to play with the numbers. Last one is the odds ratios with the confidence interval. So again, this is the same setup. Okay. So نفس السيت كمان I have 1,000 as a total. I picked 500, 500. Maybe no. Let me come back to this one when we cover the case control design, because this is set up for the case control design, not for the cohort, and I'll explain that when I come back to that in a moment. All right. So what we're going to do now is we're going to go back to the lecture, and the next thing on our plate, we're still talking about the cohort. And no, in fact, now we're just going to look at the design that is for the RCT. يعني the أو لا حتى for cohort. This can be done for cohort and for RCT. And what we're going to discuss is the attributable risk. So the attributable risk provides a crude measure of the difference in risk. Right at the beginning of the first lecture, I told you that you're going to calculate two risks, right? The risk of the outcome in the exposed and the risk in the outcome in the not exposed. And I said that you can either do the risk difference or you can do the relative risk. وكملنا talking about the relative risk and the odds ratio. Here we're going to come back to the risk difference. So attributable risk is the incidence rate in the exposed minus the incidence rate in the not exposed. Remember, incidence rate is the same as risk. So risk in the exposed minus the risk in the not exposed. That difference is going to give you something called the attributable risk. So if you go back a few slides back when I was discussing the oral contraceptives with the myocardial infarction, we calculated two risks, that of the exposed and that of the not exposed, and it came out to be 7% in the exposed and 4.5% in the not exposed. That difference is a 0.025, or in other words, is 25 per 1,000. That is the attributable risk. شو معناتها 25 per 1,000؟ يعني in every 1,000 users of oral contraceptives, there are 24 more additional cases than expected due to the fact that they are exposed. Okay? So think about it. بما أنه the not exposed, the incidence is 4.5%. يعني if they were not oral contraceptive users, هول الألف, these 1,000, you would expect to see 45 cases, because that's the incidence rate if they're not exposed. However, you did not notice 45 cases, you saw 70 cases, right? According to this. So you did not see 45 cases, you saw 70 cases. The difference between 45, which would be the expected if the exposure didn't do anything, and the actual value that you saw, that difference is the additional number of cases. Why there is additional number of cases? Because they are exposed. And therefore, that's how we interpret it. We say, like, per thousand exposed, the number of additional cases attributed to their exposure status is, in this example, 25. However, to be talking about attributable cause, you should be able first to establish causality. وعم نرجع لقصة برادفورد هيل. Notice how كيف عم نرجع لبرادفورد هيل. So before you can talk about this causality, you should be able to establish the Bradford Hill. But anyway, we're going to continue discussing it, even though as you haven't established. So in this figure right here, I'm trying to explain what I said a moment ago. So what I said, like, if you have 1,000 people, if they're not exposed, you expect to see 45. So أنا هون رسمت 40. I made a mistake. It should be at the 45. Okay. So this is what you expect to see in the not exposed. In the exposed, you saw 70. The difference between the two is what we call the attributable risk. Okay, يعني the additional number of cases you would expect to see due to the fact that they are exposed. Does not indicate proportional reduction between treatment and untreated. So على فكرة attributable risk, you can also talk about it بدل ما تقولوا these are the additional cases per thousand exposed. You can talk about the number of cases that you will save if you are able to stop the exposure. Okay. However, these values are absolute values, and what we do actually is that we turn it into a percentage. So you take the attributable risk we discussed, but this time you're going to divide it by the risk in the exposed. يعني من أصل السبعين, we just said out of the 70, 25 are attributed to the fact that they are exposed. Okay, so what is the percentage of that? So you turn it into a percentage by taking the 25 and you divide it by the 70, and therefore you have a percent. And that is called attributable risk percent. And its interpretation is very simple. So that's the formula. You calculate the attributable risk, يعني the risk difference. You divide it by the risk in the exposed, or incidence in the exposed, exactly the same thing. You multiply it by 100. This measure is used to assess the percent of disease reduction that would happen if the exposure was eliminated. So in our example, 25 per thousand divided by 70 per thousand times 100 is 35.7%. So you could say that 35.7% of the myocardial infarction cases among the exposed group are attributed to the fact that they are exposed. And therefore, if I were to stop the exposure, I would reduce the outcome in the exposed by 35%. Okay? So this is the percent attributable risk, and you can talk about the risk reduction, percent risk reduction among the exposed only, لأنه the calculation is based on the exposed. So let's do an example. Here's the lung cancer and the smoking. So if to be able to do the things we talked about, you need to calculate the risk in the exposed, the risk in the not exposed, which by now you should know by heart. The risk in the exposed is 61 over 1357, and the not exposed is 7 over 1357. Okay, you notice انه هيدا number is exactly equal هيدا number. This is just a reminder that these numbers are fixed. لما بتعملوا cohort أو RCT انتوا بتنقوا, you decide on the total of exposed and the total of not exposed. You decide, I want to follow 10,000 exposed, 10,000 not exposed, if you have the money and the resources. Okay. So in this study, they decided that they wanted equal number of exposed and equal number of not exposed. They followed them up. These are the incidents in the exposed, the incidents in the not exposed. You calculate the risk in the exposed. It comes out to be equal to 0.045, يعني 45 per thousand. In the not exposed, it comes out to be equal to 0.005, يعني 5 per thousand. The relative risk is 9. obviously. So the risk of lung cancers is 9 times greater in the smoker than in non-smokers. Now for the attributable risk لحالها بعد ما عملنا percent, you just do the difference between the two. You get 0.04, which is 40 per thousand. The way we interpret this, out of every 1,000 smoker, we are seeing an additional 40 cases than expected due to the fact that they are smokers. Okay, so think about it. In بالألف non-smoker, you see 5 lung cancer. بالألف smoker, you're seeing 45. Okay, an additional 40 cases, and therefore you talk about the attributable risk being 40 additional cases per 1,000 smoker. Now let's turn this into a percentage. The 40 is divided by the 45 times 100, that's تقريبا 89%, and therefore you talk about 89% of the cases in the smoker are attributed to the fact that they are smokers. Or if I was able to somehow stop their exposure to smoking, I would be able to reduce the number of cases and the number of lung cancers among a smoker 89%. Okay? So هيك بنكون حكينا على attributable risk and attributable risk percentage. Last, we're going to talk about شو الفرق, what's the difference between attributable risk and the relative risk. How are they different? And to do that, we're going to come in a cohort of 100,000 smoker and 100,000 non-smoker, but this time we have two outcomes. So I have the lung cancer as outcome number 1, and I have CHD as outcome number 2. And you have the incidence among the smoker for lung cancer, and you have the incidence of CHD among smokers and non-smokers. Obviously في البقوة يعني هن اللي non incident among lung cancer و non incidence in the CHD, but I'm not representing them so that I can put both in one table. The next thing I did is I calculated the relative risk for every one of them. You can calculate that. It's 140 على 100,000 divided by 10 على 100,000, so that's the 14. And it's the 6,690 divided by 100,000 divided by 4,130 divided by 100,000, so that's with the 1.6. And then you can do the attributable risk. Okay, so taking the difference between the risk, and it comes out to be 130 per 100,000 smokers, and over here it's 2,560 per 100,000 smoker. And the reason I'm doing that is because I want to show you I want to show you this. Look at the relative risk between the two. The relative risk for smoking for an outcome as lung cancer is 14, أما for CHD is 1.6. يعني smoking increases the risk of lung cancer 14 times. However, it increases the risk of CHD 1.6 times. So when you look at that, you say, oh, okay, so smoking is has a much stronger association with lung cancer than heart disease. At this level, you're right. However, since lung cancer is a much rarer outcome than CHD, if you look at the attributable risk, you notice that the number of additional cases occurring due to smoking for the lung cancer, it's only 130 case per 100,000, compared to 2,560 cases per 100,000 for the CHD. يعني مع أنه the relative risk is much smaller for CHD, the number of cases per 100,000 is much larger. Okay, so eliminating smoking is going to save a much larger people from CHD than it's going to save them from cancer. And that's the nature of thing. Yani this is totally normal because the incidence rate of CHD is much larger in both the group compared to lung cancer. So that was the last thing I wanted to discuss about attributable risk and risk reduction. Then we're going to move to something that is only calculated when you're dealing with clinical trials, and this is the number needed to treat. This is only done in clinical trials. So when you're running a clinical trial, there are 3 things that can happen. 1, you decrease about bad outcomes. So you may be treating people to prevent myocardial infarction, or you're treating people to prevent مثلا early death, or you're treating people to prevent hospitalization. So that's the case number one. The case number two is you want to create a good outcome. So you might be treating people so that they keep a healthy mood, or مثلا a healthy level of blood pressure, or a healthy level of cholesterol. So that's a good outcome. However, the third outcome, that's where the safety issue, and that's where you start getting bad outcomes. ممكن حدا مثلا يعمل seizure, ممكن حدا يعمل side effects. So these are the three possible things that can happen every time you have a clinical trial. We're going to use this concept to calculate the values in this next slide. Okay, so having that in mind, we're going to define new terms, although we already know these new terms, but it's a new definition of these terms. So instead of talking about incidence in the not exposed, or what we've been calling نحن مثلا risk in the not exposed, هون the literature you'll hear them talking about control event rate, يعني the rate of the events in the control group. This is exactly what we have seen before. Event هو outcome, the rate is just the rate, and it's into control group, يعني not exposed. So risk in the not exposed, or the incidence in the not exposed, they like to call it control event rate. However, in the exposed, they call it the experiment event rate. Okay? And the difference between the two, which we covered a few slides back, يعني attributable risk, or the risk difference, they call it the absolute difference. And they're just going to put it in absolute terms. So this absolute difference in scenario number one, remember in scenario number one, you're reducing a bad outcome, you're preventing early death. And therefore, the incidence in the control is going to be higher in the event. And therefore, you're going to talk about absolute risk reduction. You're reducing a risk. And this is ARR. Scenario number two, remember, scenario number two, you're actually increasing a good outcome. And we talk about the same value here as absolute benefit increase. However, in the last one, where you're causing side effects, it's the absolute risk increase. So they're calculated exactly the same way, but due to their interpretation, we call them differently. So ARR for absolute risk reduction, ABI absolute benefit increase, and ARI absolute risk increase. They're calculated exactly the same way. It's just that they relate to the scenarios we discussed. So come the number, the NNT, and the number of patients, or the number needed to treat. This is the number of patients you need to treat to prevent one additional bad outcome. That's scenario number one. So for example, if the number needed to treat is 5, it means you have to treat 5 people with the drug to prevent one additional bad outcome. It's useful when the treatment needs to be compared and when treatment decisions are made. It reflects the likelihood an individual will benefit from the treatment. The best thing to do is just to look at the calculation and try to do some interpretation using that, which is in this slide. So this is the case number one. Remember, in case number one, we are preventing a bad outcome. So the number needed to treat, this is the number we need to prevent one additional bad outcome. Once you calculated your ARR, absolute risk reduction, تاخدوا inverse of that, the 1 over the absolute risk reduction, that will give you the number needed to treat. وكل ما كان النمبر needed to treat smaller, that means it's a better, because you need to treat less people to be able to prevent one bad outcome. Okay, so number needed to treat for the first scenario needs to be small. That's a good thing. Scenario number two, remember, this is when you're creating a good outcome. So we talk about absolute benefit increase. Again, you take the 1 over that, and that you will get the number needed to treat to create or to cause one good outcome. Again, the smaller that number, the better, because by treating 3 or 4, you're causing one good outcome to occur. And the last one, that has to do with the safety, the side effects, and that's where we talk about the number needed to harm. So by treating this number of people, you're going to cause one harm. Okay? So let's read the slide. Disability or death may result from drugs or other types of treatment and may vary in severity according to the condition being treated and the nature of the severity of the harm. You know that anytime في RCT بيكون في safety issue. Okay? For example, a small illness such as the common cold, the chances of experiencing life-threatening event is not acceptable even if it's rare. So the number needed to harm is therefore the number of person you have to treat for one person to experience the adverse event. It is calculated as 1 divided by the absolute risk increase, and a large number needed to harm indicates that the adverse events are rare and vice versa. And here comes the calculation. You're going to calculate your absolute risk increase, which we covered previously, and you do 1 over. And again, that is going to give you the your number needed to harm, the number needed to harm, and this is the number of people you're going to treat to harm one person. And obviously here, the larger it is, the better, the safer it is. So here comes the example. The example we're going to look at is the effect of insulin therapy on diabetic patients after a long period of treatment. Scenario number 1, remember, number 1, you're preventing a bad outcome. So we're preventing diabetic retinopathy. The case number 2, we're causing a good outcome, which is the increase of proportion of patients with satisfactory HbA1c. However, the last one, this is where you're causing something bad, which is you're causing hypoglycemia. So scenario number 1, the control event rate, yani the risk in the not exposed, those not treated, هيكون retinopathy in 38%. So if you do not treat, the control event rate, sorry, I skipped, sorry, let me go back, sorry, that's where we were. Here we go, retinopathy. If you do not treat, 38% of your diabetic population will end up with a retinopathy. However, when you treat, the experience or the event rate will go down to 13%. So you're actually preventing a bad outcome. The absolute risk reduction is 25%, taking the difference between 38% and 13%. فيكم تحطوا 0.0 you're going to get 0.25, and then the number needed to treat, remember, it's the inverse, and it comes out to be equal to 4. So what does that mean? It means you need to treat 4 patients to be able to prevent 1 retinopathy. Okay, but please note that does not mean that the rest of the 3 will actually have retinopathy. هذه كتير مهم ننتبه لها. Okay, so let me spend a few minutes here so that I explain what I just said. I'm just gonna open Paint so that I can do some of the things. يلا لحظة. يلا, let's go to Paint. So you remember I said that the incidence in the non-treated, okay, so the control event rate, يعني the risk in the not exposed, or the incidence in the not exposed, I keep repeating so that you don't get confused, is 0.38, right? That means if you have 4 individuals that are not treated, how many will actually end up with retinopathy? So all you have to do is multiply 0.38 by 4, and let me do that real quick over here. So that's 4 times 0.38, you get 1.52. Okay, so if you do not treat, 1.52 will end up with retinopathy. However, the experiment event rate, يعني the risk in the exposed, or the incidence in the exposed, is actually 0.13, meaning that if you treat 4 people, how many will end up with a retinopathy? That's 4 times 13%, and that is 0.52. Okay, and this is exactly what we're saying. Okay, if you have 4 people, you expect to see 1.52 to get retinopathy. By treating these 4, you're reducing that number to 0.52, yani you are actually saving 1. And that's what the number needed to treat to mean. So by كل we treat 4 people, we are preventing one bad outcome. But preventing one bad outcome does not mean everybody else get it, okay? So I hope this example illustrates the idea behind it. So by treating 4 patients, we are preventing one case of retinopathy. Okay, so this actually I did all the calculation here. So you see the 1.52, the 0.52, and thus preventing one outcome. Let's look at the HbA1c. So the control rate, the control event rate in the non-treated is 30% only, and on good HbA1c. But when you treat them, you go up to 60%, and therefore the absolute risk, no, benefit increase, it should be here. The absolute benefit increase is 60 minus 30 equal to 30%. And therefore, the number needed to treat is 1 over 0.3, which is, if you round up, it's 3. معناتها, by treating 3 patients, we are able to control 1 case of HbA1c. كمان the same idea. When you say I'm controlling 1, it doesn't mean that the others are not controlled. لا, you're adding 1 in additional 1. So here's the calculation. If I do not treat 3, I expect تقريبا 0.9 to be only 0.9 will be controlled HbA1c. By treating, the rate goes to 60%, so that's 1.8, and therefore I'm adding almost 1 زيادة. Okay? And that takes us to the last setup. This is the hypoglycemia, where you're actually causing a bad outcome. 23% not treated بيصير معهم hypoglycemia. When you treat, this goes up to 57%. معناتها the absolute risk increase, let me fix that, is 34%. The 1 over the number needed to harm, it should be. The number needed to harm goes up to 1 over that, يعني 3. يعني by treating 3 patients, I am causing 1 extra patient to have hypoglycemia. And again, you can see the calculation here and the illustration. All right. So to put everything together, if I pick, لأنه طلع عنا number needed to treat 4 4 3 or 4 3 3. If I pick up a common denominator of 12, I can say if I were to treat to 12, I will prevent 3 retinopathy. I will cause 4 good HbA1c level. However, I would also cause 4 hypoglycemia. And by looking at that, I can evaluate the how good or bad my treatment is doing. So on the next slide, I have for you here 2 examples, applications that you can work on, see if you get the idea behind it. But the setup, just notice the setup of the table is a bit different from the way usually we set up the table. So I have the exposure here, and I have the not exposed. نحن عادة we set them up the other way around. So I did it هيك بس حتى to be able to show the 3 possible outcomes. Okay, so this is the total exposed, total treated, the total non-treated, and over here you have the outcomes occurring in the treatment and the outcomes occurring in the control or in the non-treated. And therefore, if you want to calculate the incidence, you just have to take the 150 over 1000 for the renal failure versus 300 over 1000. هلا بما انه it's 1000 you can see that for renal failure, ACE inhibitor is reducing the risk from 300 to 150 per 1000. For blood pressure control, كمان, what is happening is when you're treating those with blood pressure control, they go up from 150 to 450, so you're actually increasing a good outcome. However, intractable cough increases from 50 per 1000 to 75 per 1000, so this is the harm that you're causing. And you can calculate for each one of them the absolute difference and do the 1 over 1 over 1 over. Therefore, you can calculate the number needed to treat for renal failure, the number needed to treat for blood pressure control, and the number needed to harm for intractable cough. And you can compare your results and evaluate the ACE inhibitor. Here's another example. This is for statin versus placebo. This time, the totals are not the same. So عندكم 4,000 treated and 6,000 non-treated. The new cases in each group are represented. So again, 250 على 4,000 will give you the incidence rate of stroke among statin, and 600 over 6,000 will give you the incidence rate of the stroke among placebo for stroke. Again, incidence rate معناتها risk. You do the same thing for control of lipid profile. You do the same thing for myalgia, and you can apply everything we discussed to calculate the number needed to treat for stroke, the number needed for lipid profile control, and the number needed to harm for myalgia. And by comparing these numbers, you can evaluate your treatment. Next is an example for the number needed to treat coming from, I think it's treating schizophrenia with aripiprazole. And basically, I'm just going to show you the results from the section. I think this is the abstract, and let's go over it حتى نقدر نشوف how they did that. Despite the fact that 7,000 people participated in 15 randomized studies, we were unable to extract any usable data on death, service outcome, general functioning, behavioral agreement services, etc., economic outcome, or cognitive functioning. Study attrition was very large and data reporting poor. Compared with placebo, the aripiprazole significantly decreased relapse in both the short and the medium term. So هون عندكم n equal 300 in one RCT. The relative risk is 0.66. So if I want to interpret this relative risk, I would say that treatment reduces the risk by 34%. That's the 1 minus the 0.66. The confidence interval for that relative risk is 0.5 to 0.8. It does not cross 1, and therefore it's statistically significant. Meaning the actual relative risk in the population is somewhere between 0.5 إلى 0.8. هون بقى في عنا the number needed to treat being equal to 5. معناتها you need to treat 5 individuals with the treatment اللي هو aripiprazole to be able to actually prevent one relapse. So this is the number needed to treat to prevent a bad outcome. Okay, so you need to treat 5 to prevent one additional relapse. Again, remember ما معناتها البقوة حيعملوا relapse. Okay, وفي confidence interval for the number needed to treat going from 4 to 8. نحن we did not go over how to calculate the confidence interval for number needed to treat, but that is fine. Let's continue. It's also produced better compliance with study protocol. So better compliance, this is the good outcome. And so N is 2,271. In 8 RCT, the relative risk is 0.72. يعني there is a risk reduction in the non-compliance by 28%, with a confidence interval going from 0.5 to 0.97. It does not cross 1, and therefore it's statistically significant. The number needed to treat is 26, and therefore I need to treat 26 to prevent 1 from not following the protocol. And let's see the last one. Ariprazole may decrease prolactin level below the expected from placebo. كمان عندكم relative risk and the number needed to treat. Let's go. I'm just gonna go fast and see إذا في عنا number needed to harm. Just give me a second, يلا. So looking at the data, they're only focusing on the good side. حتى لما بيحكوا على side effects, they're comparing the medications that actually have less side effects than others, and therefore they're still looking at it from the positive side. Anyway, the idea behind this example is how you can have relative risk with confidence intervals reported and the number needed to treat as well. You can look up the literature for examples, and I'm hoping by now you have a good understanding of how this works. By now we are concluding all types of measures of association for RCT and cohort. Next, we're going to talk about what can we do in a case control design and a cross-sectional design, and therefore I'm going to have a specific lecture for that, but it's building up on everything we have covered here.